still have to learn cadence first. And I already have the circuit laid out, simulation for you guys. And I was running that simulation for 12 hours in the morning, and it works. 4-bit, that's why the resolution is so bad. If you play a music, you probably will, hear something else. All right. So we will talk about what are in here for the 4-bit for the most part of this class. It's mainly just for the timing, okay, for the timing. That's a very critical part of it, because competitors given, right? It's given. We're not designing op-amp, it's an analog circuit class, advanced analog circuit design class. It won't be covered by the microelectronics class in undergraduate, but it's a lot of times it's microelectronics number 2, right? Go to graduate school, you'll learn something like that. Small signal analysis, AC signals, those is op-amp design, but it's given, right? So we just directly copy it. Sample and hold, we covered it on Monday, right? Is that Monday? No, Friday last week. Monday or Friday?
Kind of both.
Yes.
We covered it a bit yesterday.
Sure. Okay. It's recorded. Okay, it's recorded, so you can always go back and watch the video. And R2R DAC, you have done this a lot, but now this is a 4-bit. It looks like so cute, right? It's so small. And then it's a end of conversion latch. I'm not good at naming things. I just name it as door. Door clock. Professionally, can call it end of conversion latch. It's a door. It's a door. Okay, and because whenever it's ready, you kick it out of the door. Like when you were kicked out when you were 18 years old by your mom. So it's ready. It's getting kicked out. Okay. Very simple. It's parallel in, parallel out. One rising edge clock is over here, and the clock's name is clock door. Okay, being shorted, synchronized, and it's being shorted to all the clocks. One rising edge will send it out. So you can see the D flip-flop is the one we did in the class. It's the TI version of it with the set and reset, and both of them are 0 active, right? Active 0, 0 active. I forgot this again. Too old. Which one? Active 0.
Yeah.
Right. Okay. Active 0, so which means that 0 will trigger it, right? So 0 will trigger it. Okay. This circuit we have spent, I think, a week, almost over a week, to explain every single thing. But we didn't do a quiz on it. But if you don't understand anything about this D flip-flop, go back to the videos and recap on things. Okay, so that's the D flip-flop for this latch. Okay, and it's very simple. It's parallel in, parallel out. So parallel in is going to the D's. Parallel out are the Q's. Okay, so whenever it's ready, you got a simple rising edge. Will send everything over here to the other side. And that's the data which is ready. You only want to send the ones that are ready to the output. But whenever before it's getting ready, if all the D's are changing, are they affecting the result? We spent a week on the D flip-flop, remember? So we verified all the signals on every single line. So we are trying to verify it that it's a rising edge triggered, because when the rising edge arrives, D will be copied to Q. Okay? That's the first thing we verify. And the second thing we verified is that after the rising edge, and if D changes, Q is not getting changed. So that's why it's the rising edge triggered D flip-flop. Okay? So we do need it over here because we only want to change it, only want to send it, all the D's to Q at the rising edge, but not anywhere else. So we don't really care about what's gonna happen over here before and after the rising edge, but only at the rising edge. If the data is ready, the data is correct, we send it out. So all these changes at these 4 lines, including all the intermediate values from the SAR's output. Remember, we have, if it's a 4-bit in the quiz, on the quizzes, you drew 5 states, right? Starting with 1 or zeros until the final converted result. You have 5 states. So these 5 states are actually all these digital values being held onto these 4 lines during different time frames. And all these ones that are changing, it doesn't actually matter because we're not sending them out before the rising edge arrives. Does that make sense? So the comparator, we need a trigger, we need a pulse to sample this sample hole. And what's the figure we can look at, which is this one. I'm going to work on the course project webpage, but now I'm just using the one from the last semester. So there are some issues, and I optimized it. So now we have a better timing clock to control the logic. This is definitely is going to get a better result. So, but the sample hole is not changing. You see, when the pulse comes, it samples it, right? When this one goes has a falling edge, it holds it. So the conversion should happen after this point, but not over here, or not over here, not during the pulse, right? But after the pulse. Okay, always think about this figure over here. Always think about this figure. We already figured out why it works this way from the lecture on Monday. We went through every single thing in that sample hole circuit. If you want to restudy it, go back to the video to watch it. However, we know that this is the conclusion, right? Sample and track when there's a floating VDD. And whenever it's holding here, which means that switching NMOS is getting turned off. So it's holding at the capacitor of the sample hole circuit. Scratching your head. What? That's where we need a quiz. Okay. See, it's totally different outcomes, right? If you have a quiz, you can learn it very efficiently. So this one, you hold it here, you can start a conversion. Okay, but always think about this figure. Okay. That's the sample hole circuit. You hold it, you get a result. Is there any control in between here? No, it's just op-amp. It's converter, right? It's a comparator, and the result here from the previous state, which is over here from after the DAC, right? So you have a SAR's output, and it's being converted back to analog voltage, and it's being sent back for the comparison, right? And there's no control over it. I don't have any latches in the middle. So whenever you have a voltage here, and the conversion will, so the SAR logic will run through all the clocks and eventually give you that SAR result and being sent. And you can see, what is this one? This doesn't have any control. It's just a resistor static circuit, no control. And eventually that voltage will be fed back to here and give you a comparison result. And so we will, at some point, I will let you guys, maybe Friday, so study the sequencer and code register circuit that we covered. That was 2 lectures, I think. That's required, okay? You have to know that. So I'm gonna run through that one more time because we need to go through that to be familiar with the timing. And then on Friday, there will be a quiz on code register and sequencer circuit. So what is that circuit? Do you guys still remember that? Let's go back to the videos over here. This one probably.
Yeah,
This guy.
that's the one with a bunch of D flip
Right?
flops.
Yeah, this guy, right? How this works?
Yeah, so it's basically
Yeah, so we need a sequencer on the top. So what the sequencer does is, keep in mind, this will be on the quiz, okay? So whatever I'm talking about, sometimes I pause and ask a question and require some, or demand some interaction. So that possibly will be a question on the quiz on Friday, okay? So this is a sequencer. The sequencer's job is just to provide a 1 at the very beginning and all zeros after it, right? and then it will shift that one to the right. So that's why I call the sequencer. It's sequencing it, it's shifting that one to the right. And code register is over here, is at the bottom, even though I drew it first, but actually this one should be at the bottom, code register. So this circuit should be on the top, right? Should be on the top. And this is at the bottom. All right. How this works? First, like we know, right? When all the SAR conversions happening between all the states, it will set a 1 first, and that 1 is being connected to where?
So the set of the code register.
Code register, right?
That's
Code register. Yes. Yeah, so to where? To the where of the code register? Is that weird? Think about it. So this is to do what? Is to set the first one, right? So the first one will output a 1 and the all zeros as the output of the SAR block. So where is the output of the SAR block? It's over here. That's the output of the SAR block. So at the very beginning, the code here should be 1 and all zeros. Okay? So if you go back into this block's circuit, if you need a 1 and all zeros, what you need to do over here? Set the first one and don't touch all the following ones, because by default they are outputting zeros, right? So only need to set the first one. So in order to set the first one, for the D flip-flop we have, what you need to do?
For the, you have to give it a 1.
It's 0 IP, right?
Oh, yeah, 0. So it'd be a 0.
So it should be 0.
Yeah.
Should be 0 where?
At the D pin, or the S pin.
Yeah. But what do I have over here? I put a 1 there, right? So what you want to change? This is just an example on the paper, but for the real circuit, what should you do? So that's the one on the top, right? This is doing all the setting, right? So it's basically have a code over here, and that code will set 1 by 1 in a certain sequence.
You just use Q0, so the key which not.
Yeah, just use a Q0.
Yeah.
That's right. So you use Q0. So the first one we'll get a 1 here, we'll get a 0 here, and all the rest are zeros. All ones, right? So the rest are not getting set, but only the first one is being set at the very beginning. I'm putting 1 here just make it easier for you guys as an example, right? The thing is, we're actually using Q0, not Q. Okay?
Yeah.
And while we are putting a ground over here, remember? As a sequence on the top, we put a 0 at the very beginning. Why?
I guess because we're more just trying to, I guess, rotate the output, so we don't really need to know the initial input is, right?
Yeah, because every time this one, for example, 1 is setting it, right?
Yeah.
And we need to put a 1 in front of it when we are shifting this to the right.
Mm-hmm.
We only need a 1, 1 there, right? But not multiple 1s.
Yeah.
Is that right?
Yeah, because we want to.
So the first time it sets it, get a 1, and next time we don't set it, we release these setting pins, setting and resetting pins. So these becomes D flip-flops. So it's start pumping these ones to the next stage, and then the first one will receive a 0 after it, and that 0 will ripple through the whole stage, all the stages after that. Okay? So eventually you are getting 1 and all zeros first, and then you got a 0, 1 for the next stage, right? So that's what we want to do, but definitely we're using Q0, so it's getting inverted for setting the code registers. It's just the same thing, right? Don't worry about that. You just understand this one, then you just use Q0. Use Q0 for that purpose. Okay, use Q0. So if it's a Q0, when this 0 is being sent to here, it becomes a 1, right? So 0 becomes a 1. So that 1 will not set or reset the code register. Am I losing anybody? Mm-hmm. So that's the code register. It's nothing but just setting up the code and shift it, right? Sequencer. So now this becomes available, right? It becomes available. And see, we are still using 1s to set it. Just keep in mind, it should be zeros, right? It should be zeros. So we are still using ones to set and reset it. But in your design, you want to use zeros because the default flop requires that, okay? But now you can see we start from 1 and all zeros, right? 1 all zeros. For example, 1 is going to set it, so we're getting a 1 and all zeros. And next time we shift that one, so put a 1 here because that's a little ground, will be shifted to here. That's why you are getting this little 0 here, right? And then that one is being shifted to the right, so it's going to set the second one. And that one is getting set, so we got a Q, got a rising edge, and that rising edge being used for the clock from the previous stage. And then that comparator result, where's the comparator result? It's over here. It's being directly shorted to the input of the SAR block, and that one will directly being registered at here. So after the first cycle, we are getting A3100. So it takes 4 times to eventually have A3, A2, A1, A0 at the output of the SAR block, which is here. Eventually got A3, A2, A1, A0. That's the final result. And after this is ready, you should directly put a rising edge and send it out. And that is why you are seeing that plot, right? I paused it, but you can see that's how you are seeing this plot. And if you do the math, it's actually very reasonable because 4 bits, right? 4 bits is giving you how many stages?
5.
No. No, I'm not saying the SAR stages, but I'm saying the resolution stages. 16, right? Right? And the VDD, is that 16? 2 to the 4th, right? 16 stages.
Yeah.
And you have, so this one, this is the technology file I'm using for LT Spice right here is 1 volt. The VDD is 1 volt because it's a fake model. It's not really fabricatable model. It's a 50 nanometer technology, but it's fake from the textbook. So that is a small channel technology and can handle 1 volt VDD. I think the threshold voltage is probably like 0.3, 0.4 volts. It's pretty low. That's fine. So I'm going to provide you with this design. You can look at the sizes, and if you are using 180, so 180 also accepts 1 volts, but we are probably going to use 3.3 volts, right? 3.3 volts for VDD. So just to resize all the transistors by a certain ratio, make it a little bit bigger. As long as the logic works, it should be fine. So the only thing you need to modify is whenever you see some of the outputs are becoming weird, it's not able to charge up, and then it starts oscillating, which means your output doesn't have that driving capability. For example, I had issues here, right? So you can see this is the sequencer on the top, just D flip-flop, and code registers at the bottom. And eventually I find out I have to use a buffer in the middle. So the buffer is nothing but 2 inverters. So it's basically just adding more channels to the to source current from the source and ground. It's just 2 inverters, it's nothing else, right? It's just 2 parallel PMOS is just increasing the channel. So whenever it drives things, it has more bigger channel to dump current from the from VDD. It's just a buffer. It helps for it helps with having a more reliable pulses. So I find out I need to use it, then just plug it in. It's just added in there. So these are all buffers, but nothing else, right? It's just buffers. And that's the sequencer, the co-register, like the circuit I showed you on the paper from the notes from last time. It's the same circuit, You can see I'm using Q0, right? I'm using Q0. Does that make sense? Use Q0, right? Use Q0. Okay? And because I'm not, so for the ones that I'm not resetting or setting, I just connect them to high, right? Because it's only 0 triggers it. So this is a SAR block. It's really simple, just D flip-flops. Okay. And let's come back to here. So you can imagine that we do need the signals for the sampling circuit because the sampling hold circuit requires a little pulse. Remember the pulse I showed you? Right? So there's a pulse over there. And we need a clock for the sequencer because this guy is always shifting. This guy, right, is always clocking. We need a clock over here, and we are using 2 megahertz to do it for this clock. And the pulse is definitely not 50% duty cycle. Let me show you this. Is it 50% duty cycle for sample and hold?
No.
Definitely not. Can you make it 50% duty cycle? Would that work? Yes. You just hold it and track it for a long time, which is very unnecessary, right? You want to, so this is already enough. You can see after this point, it's already tracking. It's a waste of time. I can even make this narrower. I just didn't spend the efforts on that. Whenever this is ready, it's tracking, right? You want to hold it so it's able to do the conversions. So this period is for the conversion. And you want to make this narrow and make this longer. So it's not 50% duty cycle. It shouldn't. So if I let you guys think about the timing of the circuit, where should we get started?
Well, we probably. Well, I guess how long does it take to do the conversion, right? Because it seems like that takes the longest.
You want to sample first, right? So when you want to sample to get data, right?
Okay.
So start conversion. So which pulse should come first? You see, sample and hold has a clock. Do you know sample and hold has a clock?
I think so. Yeah.
What's the clock? It's over here, right? Remember?
Yeah.
We talk about that, right? It has a clock, then it samples, right? So there's a clock for sample and hold. So we need that clock to be here first, which is, I think it's, I named it phi naught, which is this guy. That's a phi bar, shows on the schematic, but it's just a clock. It's clock, right? So got this clock comes in, you need the pulse first, right? Pulse, right? Pulse, and then the rising as a falling edge will hold it. So after the falling edge, the data is ready, according to that diagram, or according to the figure I showed you. Remember, right? After the falling edge, the data is ready. So what's next?
Well, it's the comparator, right?
Yeah, so data is available over here, right? What you want to do?
Want to compare it?
Compare to what?
Well, I guess. What's the output of the?
What's the value?
It's.
0.5 volts. If it's a 1 volt power supply, it should be 1 and all zeros, right? 1 all zeros is just half of the VDD, the full power range. So how do you get that value ready? Do you need that value to be ready before you hold it over here? We want to make it ready after you have a data ready here. Before, I mean, it doesn't help, right? Does it help if you make it ready before?
Well, if you do it after, then it has to wait.
Is it? Yeah, there will be a little bit waste over there.
Yeah.
Okay. But if you do it before, you still have to wait for this to be sampled and held, right? I mean,
Did you?
like you have a egg first or have a chicken first, right?
Yeah.
So it's probably fine. I mean, so what about having both ready at the same time?
That's
Ideal, but it won't happen. Ideal things won't happen in the real world, right? So there must be a sequence. So let's have everything well controlled. So I think it's okay if you have this one here first, and then we wait for another cycle. I'm going to show you a technique over there to save some time. But if this is ready, being held there, sometimes, just in case it's not being very stable right after the falling edge. So we probably need some hold time over there before we want to compare it with the 1 or zeros, right, at the first cycle. So it's okay. Have the data available over there, analog data to be sampled and held over there is ready. And then we start doing what? To have that 1 zeros data to be sent to this point. No. So how did we create that 1 0 zeros? What should we look at?
The DAG, right? Yeah, the code.
Yeah. So we want to make this ready, right? Because whenever this is so this is at the output so see here 1 0 0 0. So whenever this is ready, is there any control over it? Whenever 1 0 0 0 is ready, is there any control before, or is there any control that prevent this from sending back to here, being sent back to here? No, it's a DAC, it's a resistor, no control, no switch. So whenever 1 0 0 0 is ready, it will conversion ready.
Yeah.
Okay, then we'll compare. We'll give you the comp result, either A3, right? A3. Does that make sense?
Yeah.
So we make this ready. What's next?
Well, no, but that's ready, because they've compared now, right? Or,
It's not in. There's no nothing like in. All right, it won't be in, right? It's comparing and getting output.
yeah.
It's over here, right? It's ready. So we need to make this ready. How do we make this ready?
The output from the
Output over here. How do you get output from here? Like 1 0 zeros. Which step? Which step? How?
Sequencer to the code register.
The sequencer need to be, so here need to be set, right? The first one need to be set. Again, I don't want to confuse you, but let's still assume that we are using queues, right? So it's the 1 and 0 zeros. And then as is set, and all the rest ones are reset, right? So what we need to do is give a little dip. It's a falling edge. Because all these ones are active zeros, right? So you give a dip. So you can set the first one, output 1, and all the rest are shorted to the same pin, the same wire, same signal. The dip is being shorted to reset pins, right? So all the rest 4 are being reset. You are getting a 1 0 zeros over here. So you need a reset signal for this pin over here. That's a little dip, okay? So that need to happen after the falling edge of the sum and hold clock. So sum and hold, the hold being held, the data is ready, the voltage is ready, right? And then you reset your SAR block, reset it, so it's outputting 1 zeros. Okay? And that one goes through the DAC, the DAC, and comes back to the comparator's input and compares. And it's gonna generate that first comparator's output, which is A3, will be available over there at the output. All right. So is that clear for this first 2 signals?
Yeah, I guess.
So
No, I'm getting confused with the set and like if it's 0, 1, falling edge, rising edge. I can't make sense of it right now.
okay. So for this sequence register, I put a 1 here since I'm using queues, right? If I use Q not, it will be 0, 1, 1, 1, 1, 1, right? Is that clear?
Yeah.
Yeah.
Okay. So the top pin over here is a set pin. I didn't write as S here, but the set pin on the top. And the bottom pins over here is the reset pin of the D flip-flop.
Yeah.
And they need a 0, doesn't matter set or reset, they need a 0 to be set or reset. Is that clear? Okay, it's a non-gate. It's a non-gate D flip-flop. Okay, so we need a 0 to set or reset. So if we give a 0 to this pin, and because this pin, you can see is shorted, this pin, the right wire here is shorted. It's shorted to the first one set, but also shorted to the reset of the following ones. If I give a 0 to this pin, it will set the first one and reset the following ones. Is that clear? If I set the first one, what's the Q not output here? 0. Okay? So it becomes 0 and 0 ones. So the first one 0. And that 0, Q not, is shorted to where?
To the code register.
To where? To
Yeah, it's a
to S. So that 0 will set or reset. Will set, right? Because it's shorted to S. So that 0 will set the first one and output a what over here?
What?
1. But all the following ones are zeros. So you are getting 1, 0, 0, all zeros as the first output by doing that reset, right? And that reset should happen right after the falling edge of the sample and hold pulse.
Gotcha. So you want to give a 0 to that first S
Yeah.
in order to load
1
0,
zeros.
0, 0, 0,
Yes.
into.
Yeah,
okay.
and that, so this code over here is the output 3210, right? This output, which is at here, and that's auto control. There's no latches between that and the comparator. So that one will be directly converted to analog voltage by the DAC and being fed back to the inverting terminal of the comparator. And the comparison will happen. Auto control. It'll happen, right? Once that 1 zero's available, come back, compare, boom, A3 will be there. A3 will be here. Okay, A3 will be there. Right after that, resetting falling edge pulse. Okay? What's next? We're not done yet.
Well, they haven't even,
It's 4 bits.
they haven't even read it in the compare value, right?
Huh?
You do it again.
Do it again. So, where to get started? No, we're not done yet. Yes, definitely you'll do it again. So it's controlled by what?
The comparator output will go into.
So the comparator's output is being fed into where? Into the first D flip-flop of the code register, right?
Yeah.
Actually, every single D of the code register.
The sequencer will need to be running it.
Yeah, it needs to
Yeah, so this clock will run again. This clock is always on, right? So this clock will run again and do what? So it's actually
Move the one.
move.
Shift
Yeah.
the one over.
So one question here. Yeah, so that's right. So the sequencer on the top will shift that one to the right, right? And what's going to happen after that?
Then it's going to set the second register.
Yes,
of
then
the
what?
link, the second D flip flop of the code register.
Then what?
And then.
You got a 1 here, right?
Yeah.
And this one is being sent to here, right? Forming a rising edge.
which will actually,
Will register A3 to here. So you got A3,
Yeah.
okay? That's the first data to be registered over there. And then keep doing that. So you'll have A3, A2, A1, and 0 being available at the outputs,
yeah.
okay?
And that happens.
And then what?
That's 4 clock cycles
Yes?
of the
Sequencer? Yeah.
And then the fifth one it resets. The fifth one
So you're done with the conversion, right? What's next? What should follow that? Whenever A0 is available, A0 is registered, so all A0 to A3 are all registered,
and you
right?
send a-
And they're available over here already.
Yeah. You should
The next
send a
one-
Rising edge to the door.
Yes. So we got a first data over here. Okay? Then what?
Then you should
will the DAC also
close the door.
You don't have to close it. It's a rising edge trigger. There's no way to close it. You open it once, that's it, right? You're not closing it.
You have to have like a DAC.
It's a rising edge. It's done. It's nothing can go through. It's waiting for another rising edge. Okay? Then what? After that.
And then you give new data. You sample again.
You sample again. That's right. Yeah. It just comes back, right? You sample again and then wait a little bit and then you reset your SAR block, right? And then until it's done, you send it out. Okay? So now the question is how to generate all these pulses at a correct time. That's the next task, right? So that's why I gave you these figures to let you guys design the sequence. You can print as many as possible. I just randomly created a clock on LT Spice and print it out. You can start drawing on it. Let's go through that really quickly. Okay.
So we need
So you'll see why I'm using a inverse of the clock and inverse of the clock. So you can tell the major driving clock is actually the clock shorted to the sequencer, right? So that's the fastest clock we want to use. And because of that clock, we can find out at which moment we want to kick out something. It all depends on that clock. It should be all synchronized to that clock. Okay? So I think first thing we need to know how to design the counter, right? Counter. Let's go through counter design first. Easy. Easy peasy. How to design the counter? A counter is just counting, right? Just counting but not doing anything else, just counting. So we have this guy. I mean, battery numbers are just one bit. It's bit by bit, right? So there's no way that I can count at one bit. You need the multiple bits, right? If you have 2 bits, you can count up to 3. You have 3 bits, you can count up to 7. But 1 bit is just 1 to 1 to 0 1 0 1 0 1 like that, right? So you need the multiple bits. So for example, this guy, if I do this, is this a counter? Yes, it is. B0, B1. Okay, if you look at B0, B1, B0 as a binary number, 0 0 0 1 1 0 1 1, and 0 0 again. So a counter is basically what?
it's a 4-bit.
It's a frequency divider. If you divide this frequency by 2, and you form these 2 signals and combine them into one binary number, it becomes a counter. Does that make sense?
Yeah.
You can keep doing that. Now I got a 3-bit counter. 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1 0 0 0. Frequency divided by 2 one more time, you got a 3-bit counter. Okay? How do we implement it into circuits?
We have like a delay.
Oh, delay. It won't be that accurate. Right, so you see they are synchronized, right? Whenever this is a falling edge, a falling edge is a rising edge. It should happen at the same time. Otherwise, you are getting a little delay here, a difference of time. After this code, you got a 0 0 0 again, right? So it has to be perfectly aligned.
Would you do like something like the sequencer and is it default flop?
Yeah, DP flop definitely. So as I said, right, it's basically divide by two circuit, right? Divide by 2 circuit. And if you look at this one, it's always so I'm drawing this at the falling edge. You know what? I prefer rising edge triggered, so let's do this. Okay? Is there a major difference? It's probably starting from
0
B0, B1. So the rising edge, it toggles it, right? Rising edge just toggles it. So if you already have B0 as original clock, let's say 2 megahertz as our original clock, right? It's given, right? It's given. So you want to create a signal that it toggles. It toggles at the rising edge. Okay, so it's basically if you draw a state machine, it's really simple. It's from 0 state to 1 state whenever the clock arrives, right? And if it's a 1, it goes back to 0 when the rising edge arrives. So for true stable, it's a Q and Q plus. It's a Q current state and next state. If the current state is 0, see? If current state is 0, rising edge arrives, it goes to 1. If the current state is 1, rising edge arrives, it goes to 0, right? It's a Q plus. So it's like this. If you draw a D flip-flop to hold the state, which is the current state, which is the next state?
D is the current, and Q is the next.
No.
Q is the current.
Yeah, Q is the current. Why? Because Q is the output. You can directly see it. You are probing it, right? You probe whatever it is over here at Q, it's going to be the current state. Do you agree with that?
Yeah.
So what's the next state? D. When rising edge arrives, right? D comes the new Q. So, if you look at this one, Q plus is basically Q naught.
So you give Q naught to D.
Either an inverter here, or just directly short Q naught to D, right? Either way. I see people do both ways, or either way, doesn't matter, okay? Let's do it either way. Okay? So the frequency over here will be
C lec
okay?
Oh, you just do that for each additional bit.
Do that for each stage. So you got a half, a quarter, so on and so forth, right? So eventually you can form a circle, a waveform like this, and you combine those bits together, and eventually you are getting a counter from that. What's that?
Well, wouldn't so for like if you're gonna do an additional bit, the Q of the previous bit would go into the clock of the next one.
Yes. It's a clock, right? It's a clock. I got a D here. Q. Q naught. Right? So that's your data here. But interestingly, it needs to be inverted. I mean, I have to look at the simulation. It's hard to imagine why, but the signals has to be inverted in order to come from zero. So all these signals from the Qs are getting inverted, you know. So eventually you are starting from zero instead of starting from all ones, right? So that's something else you need to do to put in here. And the counter is like this, and you count. For example, we are saying, hey, the remember the sample hole? We just went through the whole process, the sample hole, and after the falling edge, the data is ready, right? And we need to go through a certain number of cycles. We need to do this again to sample another one. So in the middle, we did the end of conversion kick out of door, and we did the so right behind this, we need to do a reset of the SR, the SAR's reset, right? Set and reset. Remember, we create that 1 and all zeros code. Right after this data is available after the falling edge is ready, we do this, right? So this falling edge is active 0, so that's why this 0 will reset, set the first one, but reset all the following ones to give you the 1 and all zeros, right? Give you 1 and all zeros. And so after this falling edge, you couldn't see from the digital waveform, but the thing is, the analog voltage is being held over there. It's ready. Okay? So then you do this, what's gonna happen? 1 and all zeros will be available. And it's out of control. Okay? And to the comparison, A3 is available.
So you need to
Alright? So whenever the another clock from the SAR will register A3. Okay? So that won't happen before that until this point. Why?
because be triggered by a rising edge. Because we also need
You have to start registering your A's after this edge. Why?
because now both the hold and the SAR will be ready, so it'll have completed its reset cycle.
Yes.
Yeah.
Partially, yes. So whenever this is 0, yes, the falling edge will set and reset the SARs to give you 1 and all zeros. But if this stays at 0, all the D flip-flops are in the set and reset state. They are not D flip-flops. There's no way that it can shift anything, right? So it can only happen when you release it. So this becomes 1, and all the D flip-flops becomes real D flip-flops again. Okay, so you have to wait until this point to happen. So you can make this shorter if you want. I didn't, but you can, right? You can make this shorter by design fancy circuit. But I would just wait for another rising edge to put it back, right? And then you can do the A3, A2, A1, A0 register at the rising edge of the clocks, okay? And then once that is ready, you need another clock to do your end of conversion. End of conversion is the door's clock, right? So should that be a dip or a bump? End of conversion is one kick, similar to these bumps, right? Should be a bump, I already told you, right? So after A0, so this A3, A2, A1, A0 is going to register by each rising edge. And after that one, you need to wait another clock for this one to get a bump over here, right? To send it out. So this one will kick it out. And after that kick, if the data changes, so because your SAR's clock is always pumping, right? It may change the result a little bit or may not. Doesn't matter because it only happens at the rising edge. We just need to make sure that after this, all the A's are ready, so we just kick it out. Then it's getting latched. We worry less about other things. What else?
Will following agent not trigger the cycle? Or no?
It's ready almost at the end of the conversion because this is another sample, right?
Yeah.
What else do we need to do? So you can see this has to happen after this.
Yeah.
Okay? But in between or before or after, whatever. So what else we have to do? That's a counter. That's a counter thing. So the counter is if you have a 4 different flops counter, if you do not set a value to it, if you do not control it, it will count. If you have a four different flops, it will count until what? If you have another one, if you see this one, if you don't control it, it will count until what?
Until it reaches its maximum.
Until 7, right? See? 7. And then overflows, right? Become all zeros. You don't need to set or reset, it becomes zeros by itself. However, you can control it to only let it count to a certain value, right? And then force it to reset to start counting from 0. And that's required because we are not necessarily have to count until 16 or 15 over here. We have 4, right? It's gonna be 15. We're not doing count until 15. We want to end it earlier. If we are done, we just end it earlier. This I think is for 4-bit. It's probably like 7 or 8. Okay, so we want to count it to 8, and then we want to reset. So there should be a counter reset signal, and that reset signal, reset signal, when that one happens, it reset itself. So it will only be a dip, and that dip should happen after EOC rising edge, right? But before this guy, before a new sample is being done, right? So we want to do this. It's a really sharp dip, and that's it. Reset, so all the counters become zeros. So start counting from 1. Okay. So for example, from here, I probably it's not the right number, but from here, it's a count 1, right? Start counting 1. To this point is number 8. And for number 8, I want to reset the counter. How would you like to design the circuit to count to 8 for 4 bits of DP flops?
Maybe for I guess I need a reset.
So you have 4 bits, right? Yeah, you have to reset it, right? And see, this is the dip, which makes sense because the reset is active 0, right? So whatever the counter circuit inside, I'm not drawing them, okay? So the counters are outputting 4 digits, Q3, Q2, Q1, Q0. So these are the 4 bits. You align them like this, they're counting, right? Does that make sense?
Yes.
That's a counter's output. That's a reset. So how would you like to design the circuit to reset it, force it to reset at number 8? Number 8 is what? 1 0 0 0, right? And at this code, what you want to do is send a dip to this pin to reset it, so it becomes all zeros. So start counting from 0 again. So if you design a circuit like this, does that work? And this one shorted to all the reset pins.
Yeah. Could you not just make that a? Oh, I guess no. Actually, no.
All these are AND gates.
Yeah.
You need all ones to have a 1 here, right? For any other code, will be 0. Do you agree with that?
Yeah.
So which means it's going to be 0 for a long time. Whenever it hits 1 0 0 0, boom.
Yeah.
Okay? However, this one, all these D flip-flops requires a dip, not a bump. So anything you can change easily here to make that happen?
Yeah. Just invert.
Yes.
Just invert key.
So instead, a bump, it will be always 1. Then what's going to happen?
Randomly.
All these become zeros, right?
Yeah.
And remember, these ones are shorted to here. What's going to happen?
It'll switch it back
To 1, right?
Yeah.
Because there will be time delays of the circuits, it will. That's enough. That's the little dip. Will reset everything to back to 0, so it can count, start counting back, counting from 0 again.
Could you not make that like a single 4-bit AND for NAND?
Say again?
Could you not make that a single 4-bit NAND gate? Or
You can, yeah. Mm. All right, that's for today. And Friday we'll talk about a little bit of circuit design, but wrap up DNL, NLs, and then move forward with other things as well. And Cadence IT is working really hard on the license issue for the Cadence server. We'll figure it out. Okay, no worries about that.
And what is that quiz gonna be on again?
Quiz on Friday.
Yeah.
Quiz on Friday would be the sequencer and co-register circuit. Okay, I'm going to ask some questions on it, or let you tour the circuit. I will probably give you an incomplete circuit and let you finish it. So you need to be really good at it. Keep in mind. Otherwise, you won't be able to design the circuit. So this whole diagram, the whole circuit diagram, should be in your mind, right? You need to have an image in your brain and have all the cycles and when. What is going to happen, not just for this circuit, but also for the sequence registers and the clock, where the clock goes, the comparators pin and set and reset, all these kind of things. You need to be really good at it in order to design the ADC. Okay, so that's what I'm gonna ask you guys to study. So Friday there will be a quiz on SAR block. Okay.